So guys, this is the last of the material for this unit. Can I use this word with you? Ampersand. You guys know what that is? Yeah, guys, this thing actually has a name. It's called an ampersand. Smarter every day, right? So guys, that and symbol, which is called an ampersand, guys, this and symbol right there is a hard and. It is a this and that. Not a this plus that, not a this flowing into that. It is a this and that. So guys, to wrap up this unit, what we're going to do is we are going to talk about percent yields. This is also the lab that we're going to do on Tuesday in preparation for Thursday's test. So guys, the first thing we're going to explore is this idea of percent yield. Then when we're done exploring this idea of percent yield, the hard and, we're going to take a break from that. We're going to talk about limiting reactants, and then we're going to work on some homework today, and then you guys are going to give me your homework scores. So guys, do you understand the way this is going to play out? Okay, so with that in mind, let me set the stage for you. Don't write this down. So guys, today what we're going to do is we are going to come back to this idea that we understand that reactants produce products, right? But guys, to wrap up this unit, we're going to ask and answer two questions. Question number one is this: how much product should a reaction create? This kind of gets back to number 8 that Jared got us thinking about. So guys, the question was 1.44 grams of sodium, a pant load excess, a pant load of oxygen. How much sodium oxide can that reaction create? But guys, we're going to put a little bit finer point on this. Hey, are you Freddie? Hey, how are you? So grab a seat. We're right in the middle of getting started, and we'll get you caught up in a minute. So guys, the question that we're going to ask and answer is how much product can a reaction create? And you'll see that there's a way for us to represent that, and that is what is called a percent yield. Then guys, following up after that, we're going to ask this important question: when do reactions stop? And you're going to find out the answer is limiting reactants. So guys, we're going to pick these off one at a time. When we're done, we're done. You ready to go? Question number 1 first. How much product can a reaction create? And guys, the answer to that question, which is where you're going to start taking notes, the answer to the question, how much can a reaction create, is percent yield. Write that down with me. Freddie, let me do this for you just because you're sort of hitting the ground running. These are actually the notes, so you don't need to worry about it. You'll be good to go. That means I'm teaching without notes, so if this goes horribly wrong, I'm going to blame you. Is that okay? All right, so I'm going to try this without my notes. I may have to come over to Freddie and actually ask him to see my notes, but we'll see. It'll be fine. So guys, percent yield, let's define it. Guys, percent yield is a ratio. And when you think ratio, do you envision a division symbol? One thing over another. So guys, a percent yield is a ratio, but notice what it is a ratio of. It is a ratio of the actual amount of product that a reaction did make to how much that reaction should produce. And I know that I didn't say that just like it says on the board, but guys, maybe you'd like it mathematically, because this is actually it in equation form. That percent yield is equal to the actual yield of a reaction divided by the theoretical yield. Are any of you having a little deja vu moment? Kind of sounds familiar, doesn't it? What's it sound like? Percent error, right? But guys, once you're done writing this down, I'd like you to ask this question: how is this different from percent error? And I don't mean conceptually, I mean mathematically. What mathematical function is missing from this that is present in percent error? And we'll talk in a second once you're done writing this down. But guys, the answer to that question is the magic of what this number means. So let's talk about it. what is missing from this relative to percent error? A subtraction, right? In percent error, it's actual minus theoretical divided by theoretical. See, guys, percent error tells us how much we got wrong. That's what that subtraction does, is it compares right to what you got, and that subtraction tells you how much you got wrong. Now, that subtraction's gone. So this doesn't tell you how much you got wrong. What does it tell you? How much you got right. See, this is the happy side of percent error. This doesn't tell you how much you lost. It tells you how much you got compared to what you should have. So guys, it's the same equation, but without the subtraction, it is telling us how we did right rather than what we lost. So guys, where do these numbers come from? Well, your actual yield comes from experimentation. Today, I'm going to feed you these numbers. On Tuesday, you're going to go into lab and you're going to collect these numbers yourselves. Then guys, where does the theoretical yield come from? Here's the tie back to stoichiometry. Where does the theoretical yield come from? It is predicted by a mass-mass problem. What are mass-mass problems? The 13 homework questions that you just graded. Guys, that's why I was telling you, if you're feeling good about these mass-mass problems, you're going to be really successful with these. And if you aren't, you might not be. Because, guys, the very foundation of these calculations is a theoretical yield is a mass-mass calculation, stoichiometry. You guys all caught up with me? Okay, so here's what we're going to do. I'm going to give you steps for solving these problems. These steps are going to bring out what Sam was talking about when we were grading homework. He was like, how do I know where to start and how do I know where to end? And our answer was, start with the number, set your goal at the thing they're asking you, the what or how much question. Guys, here's what you're going to find today. You're going to be given two masses. And that's what makes these tricky. You've got to figure out which mass to start with. Here's the steps. Write them down. So guys, step number one is this. Write a balanced equation, or it'll be given to you. But you've got to have a balanced equation. I'm doing pretty good without notes, huh? Actually, it's the double whammy. Sleep deprived and without notes. Oh no, it was my choice. I just needed to make this a little more exciting. This isn't an attack. This is me living dangerously. Kind of sad, right? If this is like knife edge, you lead a pretty sad life. All right. So guys, can you answer the question why? Why do you need a balanced equation? Why do you have to have that? Exactly. You need the stoichiometric ratio. And the only place we get those is from balanced equations. So if you ain't got one of these, you can't go on. Write a balanced equation. Step number two then, and guys, this is the new stuff, if you will. This is dimensional analysis, right? We're solving a mass-mass problem. But now the answer to the question, where do we start? And the answer is always this. You will always start with the mass of a reactant. Always start with a reactant. Then what about your goal? Well, guys, your goal will always be the mass of what we call the known product. And Sam, that's why I was hesitating at the way you asked the question, because you used the word known, and I just didn't want to create confusion. So guys, our goal will always be the mass of a known product. And I know that doesn't make sense to you right now, but after you see the life-changing animation that I put together for you that I'll show you in just a minute, you're going to know. You will know. Never mind, I'm too tired to do that. All right, so then guys, step 4, solve the mass-mass problem. Jake, I think if we're not careful, I might start walking into walls. And then guys, step 5, use the result of the mass-mass problem as the theoretical yield in the percent yield equation. That's it. 5 steps. Write a balanced equation. Pick your starting point, always the mass of a reactant. Set your goal, always the mass of what we call the known product. Then step 4, solve that mass problem, which you all did 13 of or should have relative to homework. Guys, as I'm mentioning that, we need to talk about this briefly. We'll talk more next week. You understand that Orem High School falls apart fourth quarter. This place goes to somewhere else. Guys, understand that that does not mean that you cannot stay connected in here. That's what the screencasts are for. So guys, understand that when we're grading homework, the answer is, when I call for your homework score, the answer is never, I wasn't here last time. Doesn't matter. Your responsibility is to watch the screencast, do the homework, and stay caught up. That is not an excuse. We'll talk more. And I know this sounds negative. It's actually positive, because you're going to find, guys, throughout April and May, you are going to want to just come here because it's the only place that makes sense in your entire Orem High School life come early May. Like, your teachers are flaking out, the school's falling apart, shorts are getting shorter, temperatures are going up, life just gets hormone-ridden and ridiculous, and you just long to come to first period and go, thank goodness, like sense in the middle of the insanity. But guys, you need to stay focused. So, solve the mass problems, and then finally, guys, use the results of that to calculate percent yield. You ready to try one? Write this down with me. I would really encourage you to write this down. You'll be better served if you do. 15 grams of CH4 is combined. Did you notice I highlighted this word when we looked at number 8 with Jared? 15 grams of CH4 is reacted with excess. And we talked about what that means. Excess oxygen. When that happens, 32 grams of water is collected. What's the percent yield? How'd you do? So guys, once you're done writing this down, and you'll understand why I ask you to write this down in just a moment. Once you're done writing this down, we're going to go through these 5 steps. With the hopes that the things that didn't make sense when you wrote down the 5 steps become more clear as you see this play out. So again, guys, 15.5 grams of CH4. You may remember that CH4 is Bunsen burner gas. This is methane. This is the stuff that we burn in our Bunsen burners, the stuff that heats most of your homes unless you're on electric heat. This is methane gas. And guys, that gas reacts with oxygen, and it's a combustion reaction, so it forms carbon dioxide and water. The answer is, if we start with 15.5 grams of methane and we get 32.1 grams of water, how'd we do? Did we collect everything that we should have? So guys, we're going to answer this now. Here's the first thing that I would like you to do. In the problem, underline the 2 masses. You're going to find that this will save your life. But don't just underline the masses, underline the mass and then the of what. So it's 15.5 grams, and then also underline CH4. And then it's 32.1 grams, but it's also water. Underline them both so that you know where you're at. Now guys, oh yeah. You won't need to. And interesting, Ethan, you'll see why in just a moment, but you won't need to. So guys, you ready? You ready to go here? Step number 1, balanced equation. You've balanced this before, and it looks like this, so I'll just give it to you. Write it down. That's step number 1. There's your CH4, there's your O2. Classic combustion reaction, carbon dioxide and water, and it balances as written. All right. Now, guys, here's what you're going to do. Now that you've got that written down, you're going to go up into your question, and you're going to find these masses, and then you're going to write those masses beneath the components of the reaction. So let me show you what I'm talking about. 15.5 grams of CH4, write it down under the CH4. Some of you are going, really? That seems like a lot of work. Okay, but when you get them wrong, don't come talking to me. So then, guys, where does the 32.1 grams go? Obviously under the water. So, guys, why did I spend the time to do that? Well, now let's talk about step 3. Step 3? What is step 3? No. Let's talk about step 4. Solve the mass-mass problem. Guys, a mass-mass problem is dimensional analysis, right? So we need a line. Draw yourself a line. Now we can go back to steps 2 and 3. Oh, guys, you ready? Here we go. Check it out. What does step 2 say? Set your goal, or set your starting point where? The mass of what? A reactant. Okay, so which one is that? Is that the CH4 or the water? Watch close. Don't look away. You ready? Come on. That's not bad, right? So, guys, that is the reactant that we're starting with. Why don't you do that with me? You can't. Do you want scissors? You could cut it out and slide it down and then tape it. I am delirious. Okay, now guys, watch this. What is our goal? Step 3. What is our goal? Well, it's a mass problem, right? It's a mass, but a mass of which one? Is it a mass of the carbon dioxide or the water? Water. Why the water? What does it mean to be a known product? It's the one that you know the mass of. And we know the mass of water. But what does that mean? What does that 32.1 mean? It means we collected 32.1 grams of water. So what we want to do then is this. We want to bring this down, and we want to say, okay, we want to solve for grams of water. But you're going, wait, we already know the mass of the water. Well, no, we know how much we did get. What we're trying to figure out is how much we should have got. And that's what the mass-mass problem allows us to do. Now, guys, because there was a high degree of silence as we graded the homework, I feel comfortable doing this. We now need to solve the mass-mass problem. Again, it's a rhythm. Grams to moles, moles to moles, moles to grams. 16.0 grams of CH4 is 1 mole. Carbon's 12, hydrogen is 1. Do the math. Then, guys, after that, the new bit that you learned from the screencast previously, we need a mole-to-mole ratio. Moles of our starting point goes on the bottom, moles of our goal goes on the top, and then we need the numbers from the balanced equation. In front of the CH4, there's nothing, so it's an understood 1. In front of the water, there is a 2. That's what you learned last time. Then, guys, our last step, grams to moles, moles to moles, moles to grams. We got to go back to grams. So we bring down moles of water. Oxygen is 16, hydrogen is 1. Add them up, that's 18 grams of water per mole. Now we do the math, and the answer is 34.9 grams. Now do you get it? Guys, what is 34.9 grams? What we should have got. Guys, when you react 15.5 grams of methane in all the oxygen you need and more, we call that excess. When you react 15.5 grams of this with a pant load of this, you should get 34.9 grams of water. Did we get 34.9 grams of water? How much did we get? 32.1. What is that as a percentage? Well, guys, let's calculate it. Write it down with me. Percent yield is equal to actual divided by theoretical times 100. Here come the animations. You ready? So, equals. We're going to be working from left to right. So guys, the first thing that we need to do is we need to figure out our, I think theoretical, I don't remember which one I did first. So we need a line. And then guys, we need to figure out our actual and our theoretical yields. So let's take a peek. Let's start on the top. Guys, the numerator is actual. How much water did we actually, and watch the board, how much water did we actually produce? So look at what we do. We bring that number down. So we actually produce 32.1 grams. Now, in theory, how much should we have produced? Right, from the mass problem, bring that number down, do the math, 1 significant digits, and it's 92%. Now guys, that's a big number. Is that good or bad? That's good, right? So what was your percent error? 8%, but that's not what we're calculating. So we want to know how much we got right, and that's 92%. Please. All sorts of stuff. So guys, let's talk about it for a second. What keeps you from getting 100%? Sometimes it's incomplete reactions. Sometimes it's what we call side reactions. Sometimes a reaction can produce multiple products. And if you want it to only produce one product, you're trying to keep it from producing the other product. And the extent to which it makes a little bit of this is the extent to which it didn't make that. And so actually that's what chemical engineers do. The job of a chemical engineer is to take reactants and turn them as efficiently as possible into products, because that's how your company makes profit. They pay for the reactants, they sell the product, and as much reactant that you can turn into product, it maximizes your profits. So that's what chemical engineers do. So Marcos, go ahead. Darn you. I like this kid. Guys, is it possible to get higher than 100% yield? Why not? Says who? Law of conservation of mass. Guys, I know this is going to come as a surprise, but none of you have quite yet reached demigod status. And guys, what does it mean if you get higher than 100% yield? It means you made matter. I know, I'm glad you chuckled. You can't do that. Guys, it is impossible to get higher than 100% yield because you can't make more than you're starting with. But now you ready for this disturbing thought? Guys, in lab on Tuesday, more than 50% of you, when you're done with this calculation, will find that you got higher than 100% yield. And no, that does not mean you became a god over the weekend. So guys, what explains it? How we just established that it's impossible, right? Law of conservation of mass. You can't have higher than 100% yield, but 50% of you or around that are going to. What explains yields higher than 100% if it's impossible? What? Not mathematical error, that's just dumb. Not human error, that's just dumb. Not scientific error, because that sounds not dumb, but that's still dumb. Guys, what explains it? Not the measurements. Contamination. It means that your product is not pure. It means that you've got something in your product that isn't really your product. And as a result, you're not just weighing the product that you think you are, you're weighing contaminants, and those contaminants make it heavier. Keep that in mind when you do. That's actually one of the questions on the conclusions of the next lab. So that was a great question, Marcos. So guys, this is the hard and. We are now done, or at least I think we're done, with percent yield. Questions, things you want to pursue here? You're okay? Okay, so let's do the hard and. Guys, the next thing that we're going to do, the last thing that we're going to do for this unit is limiting reactants. So guys, allow me to define this for you. A limiting reactant is defined as the reactant that is completely consumed in a chemical reaction. So guys, let me, well, you're writing, and then we'll talk. Ralph, do you know what time we're done with first period? Okay. I'm sorry? It's like 50, it's an hour. It's a long one. Yeah, it's the election assembly. Okay, so guys, check this out. Ready? Chemical reaction. What I'm going to do is I'm going to light this match. It is a reaction with oxygen, but it's technically not combustion because paper, cellulose, is not a hydrocarbon. It's actually more like a carbohydrate, but it's still paper reacting with oxygen. Tyler got awfully excited about this kind of stuff on Monday in class. Apparently he's like a fireman. But, so guys, we're just going to let this... I know. What was that thing you just did? Oh, your foot. Isn't that amazing how fast your brain goes, wait, I put sandals on this morning, I might die? Yeah. That was pretty good. This is why I don't smoke. Okay, so guys, we're going to let this burn. And we're just going to let it burn. So what's reacting right now? Hold on, guys. Don't miss this. What's reacting right now? Oxygen and paper, right? And eventually this is going to stop. So what did we run out of? Paper. Thank goodness paper is the limiting reactant, right? I'm glad that some of you are chuckling. Because guys, if the limiting reactant was the other reactant, we'd all be dead, right? And guys, that it is actually kind of funny until you realize that's why a lot of people die in house fires. They don't burn up, they suffocate. Because the fire is consuming all of the oxygen in the house, and consequently there's no oxygen left to breathe. But guys, in this simple example, it's the paper that was the limiting reactant. And does that jive with your understanding of the definition? That the limiting reactant is the reactant that is completely consumed. And in this simple reaction, the paper was completely consumed and the reaction stopped. So with that understanding, explain to me why we call this the limiting reactant. Limited. Yeah, it limits the extent the reaction goes. When you're out of this guy, it's game over. So the limiting reactant is the reactant that you run out of first. And therefore, it limits the extent of the reaction. Does that make sense? Okay, so guys, with that, with that said then, let's kind of include that thought in our understanding. So guys, the limiting reaction is called the limiting reactant because it limits the extent to which the reaction takes place. So with that being the case, then that guy a name. We call that the excess reactant. So to bring this all together, when you burn a match, the match is the limiting reactant, and oxygen, thank goodness, is the excess reactant because we have all the oxygen that we need and more. Does that make sense? Okay, now guys, here's the problem. When you're burning a match in a world full of oxygen, it's pretty easy to figure out the paper's going to run out first. But what do you do if it's not so obvious? What do you do if it isn't so clear-cut which is going to be your limiting reactant? And guys, it's at this point that we need to start taking the match and turning it into something more chemical, if you will. So we are going to talk about a reaction, and we're going to talk about we're going to talk about, and write this down with me, we're going to talk about, and guys, you actually don't need to skip lines. You can write it up high. We're going to talk about which one of these is the limiting reactant. So the reaction, and you'll notice I spread it out a little bit. You'll see you don't necessarily need, well, it couldn't hurt if you did. Maybe do. It's up to you. So guys, we've got F, fluorine, plus W, two of them, W, which actually interestingly is tungsten. Tungsten used to be called wolfram, and that's where the W came from, and they changed it to tungsten. Don't know why. And then S, of course, you know, to be sulfur, and that produces bismuth. So, guys, going back to what we already know, what kind of reaction is this? Single, double, synthesis, decomposition, combustion. What type of reaction is it? It is a synthesis reaction. And how do you know that this is a synthesis reaction? What makes it that? One product. Does that make sense, y'all? Okay. But I'm noticing that you're a little hesitant. How come? Because you guys all, of course, knew this, right? That if you take an atom of fluorine and 2 atoms of tungsten and an atom of sulfur, and if you react them together through a synthesis reaction, you all understand that you're going to get bismuth, right? No. Because, guys, this is actually not a chemical reaction. This is the recipe for something near and dear to my heart, bicycles. Because to build a bicycle, you take one frame, 2 wheels, 1 seat, bolt them all together, and you get a bike. Do you love that I snuck in the bicycle thing?
Yeah. I feel like that was your plan all along.
No, I just made it up just a second ago, and yeah, it was my plan all along. Okay. And guys, obviously, this is wildly oversimplified, but for argument's sake, we are going to suggest that to build a bicycle, you need 1 frame, 2 wheels, and a seat, and you bolt them together and you get a bike. Okay, now, I want you to think about this with me. So, my son, Cody, 16-year-old, we had a little household trauma last night. My son, again, is a 16-year-old and can drive, is realizing that this is going to be the money summer. He can get a job and he can drive there. So his mind is all about summer employment. I want a job this summer. And the holy grail for Cody for summer employment is lifty at Sundance. It's been his dream since I started skiing with him when he was 3. I want to be a lifty at Sundance. He knows he can't do it during the school year, although like the Shinneke brothers pull it off, and I don't know how. But he's realizing you can't quite pull this off and be a student, although I don't think Ian and Hunter have many classes right now. But anyway, all of that to say. And so my son got on the Sundance website last night to apply for a summer lifty job. You got to be 18. Crushed. So what's he going to do? So guys, my suggestion, and that actually did happen, but my suggestion is going to be this. Cody, why don't you see if you can get a job at a bike shop? Any of you work in bike shops? Okay, so this might be the way this goes down, and this is how you're going to connect to this information. So Cody walks into Mad Dog, and he goes, "Hi, my name's Cody. I'm drug-free, and I'd love a job." And they say, fill out the application, and they fill in, and hey, calling back, good news, Cody, we'd love to have you come work for us. And as a new employee, you don't get to talk to customers, you don't get to be out front. We are going to take you deep into the back room of our storeroom, and we're going to have you build the cheap bikes that we sell to the average Joe that walks in off the street. Now, guys, these cheap, and they actually do this. Guys, these cheap bicycles, because they're inexpensive, that when bicycle shops order these cheap bikes, they don't order the bike. They order bike parts, like frames and wheels and seats. But the thing that's interesting is when they order those parts, because all these things get shipped over in containers from China, guys, they don't even, they order them by the pound and not the part. So here's the way this goes down. Cody walks into the back room at Mad Dog. They hand him a set of Allen keys and a screwdriver, and they tell him, start building bikes. And so Cody walks into the back room, and there are literally shipping containers full of bike parts. And he walks over to one of these containers, and it says 120 pounds of frames, 100 pounds of wheels, and 50 pounds of seats. Here's my question to you. How many bikes can Cody build? How many can he? I want an answer. How many bikes can Cody build? Did you hear what Sam said? And I know some of you are thinking, guys, why can't you answer the question? And more importantly, what information would you need to know in order to be able to answer the question? How much these parts weigh, right? Because guys, when we say one frame, two wheels, and one seat, that does not mean a pound of frames, 2 pounds of wheels, and a pound of seat. It's not a mass thing, it's a particle thing, it's a part thing. So what do we need to know in order to figure this out? How much does a frame weigh? How much do the wheels weigh? How much do the seats weigh? Because what can we do with that information? Find out how many of each of the parts we've got. So guys, here's the data that you need. Frames weigh 20. Remember, these are cheap bikes. Frames weigh 20, wheels weigh 10, seats weigh 2. Guys, what are we going to do with those numbers? What are we going to do with that number, 20 pounds per frame? Divide. Let me roll. So guys, when we do this division, we find out that 20 pounds of frames is actually 6 frames, 100 pounds of wheels is actually 10 wheels, and 50 pounds of seats is actually 25 seats. Do you see how we did that division? Now guys, the same question. How many bikes can Cody build? 6? 6? What's the problem? Yeah, see the problem, guys? Yeah, we have 6 frames, and yeah, we've got 10 wheels, and yeah, we've got 25 seats, but why can't we build 6 bikes? Because you need 2 wheels for each bike. So guys, and check this out. What we've got to do then, guys, is we have got to divide by these numbers. We need 1 frame per bike. We need 2 wheels per bike. We need 1 seat per bike. And when we divide by those numbers, we then realize that we've got 5 sets of wheels, and we will only then be able to build 5 bikes. What does that make the wheels? The limiting reactant. We will run out of wheels first. What does that make frames and seats? Excess. Do you get the connection now? Jake, you were going to say something. Cool. Okay, so guys, can I bring, I know you're taking notes, but I'm going to give you something more important to write down in a minute. Can I bring you back up here for a second? Because guys, doesn't this just make sense? Check this logic out. You were given the masses. You knew how much wheels you had. Weird sentence, right? But you knew how much wheels you had, but that data was worthless to you because you needed to know how many were represented in that mass. So what did you do? Well, the first thing that you did was account, don't write this down. You accounted for the mass of the parts. But then we weren't done, because we also had to account, oh boy, there's the word. Let me get out of the way. We had to account for the stoichiometric ratio. 1 frame, 1 wheel, and 1 seat does not make 1 bike. It's 1 frame, 2 wheels, 1 seat. That's a stoichiometric ratio. Now guys, in the same way, we need to apply this logic to elements and compounds. And that's all we're going to do. We're going to account for the mass of these things, and we're going to account for the stoichiometric ratio. Now guys, how do we account for the mass? What we're going to do is we're going to convert to moles. How do we convert to moles? We divide by the formula mass. In the same way that we divided by the weight of a frame to convert to particles, if it's an element, we're going to divide by the weight of the element to convert to particles. in the unit's moles. So the logic that you're going to use chemically is exactly the same logic you used at Mad Dog Cycles. So guys, how does it work? It goes like this. Step number 1, write a balanced equation. Step number 2, convert mass to moles. Don't write down the thing in green or in blue. But guys, this is what we're talking about. We're talking about accounting for different masses. Then what are we going to do? Well, just like the Mad Dog problem, next we're going to divide by the coefficients, because this accounts for the differing stoichiometric ratios. Then guys, from there, whatever number is smallest is the limiting reactant. So we're going to solve one of these together. And then you'll have 10 minutes to work on some homework. Guys, when I see you on Tuesday, we will do a lab, not over limiting reactants, but over percent yield. Then Thursday's your test. It's coming fast. Fast and furious. You guys ready to go? Okay, so here we go. I don't know that you need to write this. As a matter of fact, don't write it down. But read it with me. 25 grams of HCl reacts with 25 grams of zinc to form zinc chloride and hydrogen gas. Sound familiar? It was the third in lab? Was it the third or the third? No, it was the fourth, because it wasn't the one where the green powder turned black. It was the one where you dropped the zinc and the hydrochloric acid, collected the hydrogen, and boop. Yeah. So, guys, this is, boop, it's that reaction, right? Can you picture the chunks of zinc? Can you picture the hydrochloric, and your forms hydrogen gas, zinc chloride. You balance this equation already. Do write that down with me. But now, guys, we need to figure out which one of these are you going to run out of first. When you put 25 grams of zinc in 25 grams of HCl, when does the bubbling stop? Well, when the reaction's over. So the question is, which one are you going to run out of first? And you're going, wait a minute, you got the same amount of both. Won't you run out of both of them at the same time? No. Because in the same way, if we had 100 pounds of frames and 100 pounds of wheels, we're not going to run out of them at the same time because they don't weigh the same. Same thing here. You've got 25 grams of hydrochloric acid, 25 grams of zinc, but we don't know which one we're going to run out of first. So let's figure it out. Guys, solve this like me. It'll make them easier. Write this down. 25 grams HCl. All we're doing is writing down our masses. But now, guys, check this out. Skip 3 lines and write the other mass directly beneath it. 25 grams HCl, 25 grams of zinc. What's step 2? Convert mass to moles. Bump, 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 bump. You starting to get a sense of why that was the only essential from the previous unit? Ethan, you asked a question earlier. What was it? Oh, that's right, the excess. For some reason I had in my mind it was a question we needed to come back to. Never mind. Guys, notice we're being careful with significant digits. Notice that this calculation looks a lot like an empirical formula calculation. Remember those on the previous test? Remember how many points that you missed because you blew off significant digits? Can we not do that again? But guys, here's the hazard. Some of you are going to get into the middle of this and you're going to get all excited and you're going to think you're calculating an empirical formula. Notice how this is different. All that we've done is converted to moles. So let's see what we know. In 25 grams of HCl, there's 0.68 moles of HCl. In 25 grams of zinc, there's less zinc, 0.382 moles of zinc. Why is there less zinc in 25 grams than there is HCl in 25 grams? Zinc weighs more, right? If you've got 25 pounds of bricks and 25 pounds of feathers, you've got more feathers than bricks because bricks weigh more than feathers. Guys, the same thing here. Zinc weighs more than HCl, so 25 grams of zinc only contains this much zinc. 25 grams of HCl contains more HCl because it weighs less. So does that mean that we're going to run out of zinc first because we've got less zinc? We don't know yet, because what haven't we accounted for? The fact that 2 hydrochloric acids react with 1 zinc. So that's our next step. We divide by the coefficients. The mistake that you may make is you may get to this next step and divide by the smallest number of moles. You're not doing an empirical formula. Be careful. So guys, you divide by the coefficients, and look what just happened. Right. Which one are we going to run out of first? The HCl or the zinc? The HCl. Because guys, look, this is a smaller number. 0.343 is smaller than 0.382. This is the one we run out of first because there's less of it when we account for this 2-to-1 ratio. Now guys, understand, if we had stopped right here, we'd be wrong. Because at this point, it looks like there's less zinc. There is. But because it's 2 HCl's to 1 zinc, this is the one we run out of first. But guess what? You're not done. Because we're not done. Because if you write this on the test, you don't get credit for it. Because guys, the question does not say 25 grams of HCl and 25 grams of zinc. Do some math. What does the question say? What's the limiting reactant? You haven't answered the question yet. You have to interpret your calculations. So guys, the last step goes like this. This is the smallest, so that's your limiting reactant. If you don't write the sentence, you don't get credit. And Emmy, I know you need to go. Get out of here. Ralph, are you leaving as well? Okay. Yeah, guys, if you got to go for the assembly, we are now done. Your homework is homework assignment number 4. We do have 10 minutes. I'm going to ask that you work on this during those 10 minutes. And then, guys, we go directly from here to the assembly. Yep.